Okay, let's continue with the actual code. So let's open up the main.c, and this time I'd like to talk a bit about the timers that the OS uses, the WSF OS. I'm gonna talk about the OS a bit later, but first there is quite a bit of setup required for the OS to work properly, schedule the tasks and such. So first of all, the most important part is actually scheduling the timers. So this function does that, scheduler timer init, timer init. Oh, and again, I can't type. Here it's called in the main function before the main loop starts, somewhere here. So let's take a look what it actually does. So in order for the WSFOS to work properly, you have to set up two timers. One is a continuous timer, so the C timer stands for continuous timer, and okay, that one actually sets the one shot. The continuous timer is here, but it uses the timer B for that and sets it up for 512 megahertz speed as a continuous timer. So when it hits the I think it's 16-bit timer, so when it hits the value of 65,535, then it loops again and starts from 0. So that's a reference clock that is used by the WSFOS, but it's actually scaled down again. Here is 512, but it also uses another scaler, but I'm gonna get there. And then again there is the first of all, the B timer is the continuous timer, and then there is the interrupt timer used to wake up the processor when something needs handling. Specific process needs to actually wake up and do its work. So here is also enabling the interrupt for the timer, for the timers, and then it starts the continuous timer. It only sets up the interrupt timer here, so the timer A is here set up for once, but it's never actually started here. And also this one also registers an radio timer handler, and I think I got that from the example, but it's not necessary for me. It only toggles the LED, and I did it mostly for debugging purposes. So this setting up part sets two clocks. One set to 512 hertz, and here I left some comments saying that it uses LFRC clock, which is 1 kilohertz, and it's always on. I hope that's true. Haven't looked into that in a while, but I assume it's true. So the output is 512 hertz, which means that it's basically 1K divided by 2 for the prescaler. The same is done for, then there is the continuous timer, that's the interrupt timer. Then there is the continuous timer, but that one is set up the same way, 512 hertz. And I think not much more is set up here. The interrupt handler is registered, enabled, and that's that. So what's important is that we use those in the update scheduler timers function to be able to actually read the values in the timers and see what's going on. So here we actually read the continuous timer, so the reference timer, and we save it into a current time variable. Here we need to check if we the continuous timer overflowed once, will overflow again. so it can overflow once, and if we are afraid that we might overflow again, then we'll have to wake up only to update the timer values. So here it is, current time bigger than last time, and it's either gonna be the let's see, let's draw it because it's hard to explain. Yes, cool. Okay, let's delete this. So we have our time and we have the current time, no, the last time and the current time. So if the current time is bigger than last time, which is the situation here, so I'm looking at this part of the code. So if current time is bigger and or equals than the last time, then then elapsed time will be this, which makes sense. So that's how much time elapsed since we last woke up the processor. So in other case, we can have like the last time here and the continuous timer overflew, so filled up and started back from 0. So the continuous timer was here and it was still running, and then it overflowed on the other side and from the 0, started counting from the 0 and came here. So now we're in a situation that if we the current time is smaller than the last time, so here is like, that was our first case, that's what's gonna happen to elapsed time. But if we overflow, so we take the entire period, we remove the last time from it and we add this one. So that way we have the elapsed time is from here to here, which is technically correct, that the amount of time that has passed. This part plus this part. The thing is that if we were to overflow twice, then we would lose part of the time, because we can only count to the full period, and after that we would have to track how many times we overflew. And instead of doing that, we just wake up in order to actually reset the clocks, like set them, update them. Okay, then we actually take the elapsed time and see how many WSF OS ticks happened. That's because again the OS is again scaled. So if we take this one, yeah, it should be somewhere up here, yeah. Let me see, clock ticks per WSF ticks, yeah. So again, this number is divided by 5. So if we go back there, where was that? Here. If we divide that elapsed time, so those ticks, over this one, if there's something left, so if after scaling there is still ticks left for the OS, then we have to update the timers in the OS and save the last time as the current time. So we pass the scaled value, because the OS is interested in the scaled ticks. Let me close that one. Yeah, so update scheduler timers. This is continuously fired in the while loop. While then there is, so we update the ticks for the OS based on the continuous timer. Yes, we update, because in the end the goal of this function is to basically update the timers in the OS, because basically OS timers keeps let's say OS keeps different tasks, and those tasks have like ticks until they should be just, let's say, task 1, and that's like the ticks that it still has to go through for each task to be able to say, oh, okay, I need to execute that task. And every time we update that clock, we call WSF timer update based on those ticks. It will just decrease those every time we call it, if enough time has passed. I mean, by if enough time has passed, I mean that this value will be bigger than 0 here. Then it will remove that amount from the timers. And if a timer like this one, for example, this task's timer reached 0, then it will actually perform that task. It's like a basic timer process scheduling thing, nothing fancy. So yeah, this will update the internal timers in the WSF OS. So let's go back to our while loop. So it updates the tasks, then the WSF OS checks if goes through those tasks and see if something needs to be handled. Some things need to be handled based on the OS timer events, so this will be this one. I have basically looked into this function and it handles 3 cases. Message queue events, we can push a message into a queue. I'm gonna go through it more in detail when I get to going through the OS itself. Then there is the timer event, so just what I just showed you, when the timer reaches 0. And there is the handler event, and that's when an event is set for a specific handler. We'll get there. It handles those, then it sets next wake up, and that's actually, again, this one uses the interrupt timer, so it uses the timer A, if you look here, and what it's doing is that it stops it, it clears it, time running, yeah, it can stop it and clear it as soon as it triggers, because that's set next wake up. Yep, it's as soon as the tasks are handled, it clears this timer. It checks when it should. Actually, it's well described here. It only checks the first one, I think. Yeah, because when you insert a new timer to the timer collection queue, then it sorts them, which means that the first timer is the timer that we're gonna fire as the first one, like the soonest. So it just fetches how soon it will do it, and again in the OS ticks value. So here again we have to multiply it, because if we ask OS about the ticks, it will give us the divided value. So here again we have to multiply it to compensate it, and we set the period for it to trigger. And if there is no expiration, again according to the OS, like there's no event to handle, timer event to handle, we set it to the entire period divided by 2. That allows us to be sure that we're not going to overflow more than once. And then we started with here we set the period for that timer, and then we started, which means that we have set up the next wake up event. The processor will wake up to handle that when the timer expires. If we go to the while loop again, so at this point we have updated the timers for the tasks, we have handled the tasks that should be handled, we have set up a point in time where the processor will wake up because an event needs to be handled. So then we can turn off the other interrupt events. This won't disable the actual interrupt that will wake up the processor from the timer. We can actually see what it's doing. This one is a HAL layer thing, so we should look into one of those. Oh, it's basically written in assembly. You would have to go through the documentation of the processor to actually see what it disables and what it doesn't disable. Then I also turn off the ITM printfs. I don't know if that's necessary, if that saves energy or anything, not sure. It puts the OS to sleep if OS is ready to sleep. And next part I'm gonna go through the OS exactly to see what that means. So we can put the core to sleep. The cortex-m core, because you basically put the cortex-m core to sleep, but other parts of the entire chip still work, which means that it can actually wake up the core. I didn't go that deep into sleep modes, but that's something I probably will need to research more, because that's good for proper energy saving. Then after, I assume here you put the core to sleep, here exactly, and that means that, hey, for now go to sleep, and as soon as you wake up, call this, enable the printfs, and enable the master interrupts. And then we go back again to update the schedule timers, handle what's necessary to be handled, handle events, timer events when a timer for event hits 0, specific messages. Again, set next wake up and go to sleep. This part is basically going to sleep. This is actually waking up. And that's most of it. That's the while loop, and I think that's all there is to the timers itself, to the underlying timing, and that part is very important to understand the OS itself. So if you look at this exactly stack in it, this is the main part where handlers are set, a lot of specific handlers, and those handlers are what's working underneath the WSF OS, and a lot of those things are very opaque. It's hard to actually figure out exactly what works with what, and that's the main difficulty with working with it. There is no good documentation for that. A lot of those parts are pretty direct, as in HCI or L2C are parts of the Bluetooth stack, and they need to be there, so they are like those parts of the stack are properly handled, but it's not that clear cut, and basically this part of the code has been copied and modified by me slightly. So next time I'm gonna go through all those handlers, but by now you should at least understand that underneath it all are, let's go up, are two timers. One continuous timer, which is used as a reference clock. Then it's again pre-scaled for the OS. It's divided by 5, I guess. So the OS, assuming looking at this value, since this clock runs with frequency of 512 Hz, and if we divide that by 5, we get the actual frequency with which the OS runs. So that would be 100 Hz. Yeah, so there is the reference clock, and then there is the clock used for waking up. So it's just set up with a specific period and saying, hey, wake me up in this amount of time, so I can either update the clocks so we don't overflow, or I'm gonna handle a timer for a specific event and I'm gonna handle its functionality. Yeah, I think that's it. Let's end here, and next time I'm gonna show you a bit about the WSF OS and what's necessary to set up so the Bluetooth works properly. Okay, thank you.